Alright, welcome to the first lesson of Unit 7. Today we're going to calculate the area under a curve using left, right, and midpoint Riemann sums and interpret the meaning of these sums in a real-world context. So that being said, let's go ahead and get started. Alright, so to help make sense of why we'd want to find the area under a curve, we're going to go ahead and complete this discovery problem. So a car drives along a road at a constant rate of 15 miles per hour from 9 a.m. to 11 a.m. Go ahead and answer questions A, B, and C. Take your time with them, and then we'll go ahead and talk about it. So the first thing that we notice, of course, is that we're given the velocity. It's a constant velocity of 15 miles per hour, and the trip lasts for 2 hours. So to compute the total distance we've traveled, we can take advantage of the relationship between distance, velocity, and time, since this is a constant velocity. So all we have to do is multiply the velocity that we're traveling times the amount of time, which is 2 hours, that we're traveling at that velocity, and then we'll get the total distance we've traveled. Very simple calculation. We have 15 miles per hour times 2 hours, and we're left, of course, with 30 and then miles. And this is a very simple situation. You can do this in your head pretty easily. And the reasoning makes plenty of sense, right? I'm traveling at this velocity, and I'm never changing from that specific velocity. And so if I have 15 miles per hour as my velocity, and I travel for 2 hours, I'm very clearly going to travel a total distance of 30 miles. Now we want to go ahead and graph the velocity of the car over time. And I've set up the graph for us here to the right, so you can copy that down if you haven't already. So knowing, of course, that the velocity of the car is 15 miles per hour, I know that the graph of the velocity is going to be a perfectly horizontal line because the velocity itself is never changing. It's constant. And so it'll be this horizontal line with a y value of 15 between the times of 9 and 11, as shown here. Now that I have that, I can find the area under the velocity curve. This is the velocity curve, even though it's a straight line, and above the time axis. So I think about this area below the curve and above the axis that measures time between 9 and 11 a.m. And what do we notice about the area and its relation to the answer we found in part A, and why should this make sense? So let's first go ahead and find the area. Okay, so this area that we're looking for is the area enclosed here. And we can notice that this is a rectangle. So the area that I'm trying to find is, I'll shade it in here, is simply that area there. Well, you'll notice a couple things. The first is that the height of this rectangle is 15, and the width is 2. So to find the area underneath the velocity curve and above the time axis in between 9 and 11, I simply have to do 15 times 2. Now, we notice that when we computed the area of this rectangle, we got the exact same value that we did in part A when we computed the total distance traveled. And in fact, not only did we get the same answer, but we made the same computation, 15 times 2 and 15 times 2. And this is where the connection lies. When I find the area underneath the velocity curve and above the time axis, I'm actually doing the exact same multiplication. I'm multiplying the height of this rectangle, which corresponds, of course, to the velocity that my car is traveling at, because the height is dictated by where my curve is at on the y-axis, 15. And I'm multiplying then by the width of the rectangle, which correlates exactly to the time elapsed. So I have 15 times 2, which is 30, and that's going to tell me the total distance traveled. And this relationship was a major discovery in calculus, and that discovery is simply this, that the area underneath a velocity curve is going to give you the total distance traveled in that time period. And this extends actually to a general case, which is that for any rate of change, if we find the area under a curve that represents the rate at which something is changing, we'll know the total amount. That area will tell you the total amount that substance or that quantity has changed. Now, you may think that that's completely crazy, but to help you understand why this makes perfect and total sense, go ahead and turn in your book to page 270 and complete example number 1. This example talks about calculating the amount of snowfall that's happening. Read through it, try and work through it on your own using the figure in the book, and then read through the solution. And if you want, you can try the exercise that they tell you to go ahead and take a look at in the book. Hopefully you found that example interesting. What it does is it shows us how, even though we're looking at a rate of change which is a little different, inches per hour or snowfall, and we're looking at a rate of change which isn't constant the whole time. Notice that it's increasing, then constant, and then decreasing. We can still use the same intuition as before to find the total amount of snowfall by looking at the area underneath the curve. And hopefully you thought a little bit about why that makes sense. And maybe at first it was a little sort of why the heck does this work? But if you think about it for a little bit, it makes perfect sense. And we'll talk about this in more detail in a second. But to find the area under this curve, we have to do a little more than just find the area of a rectangle. We also have to find the area of these triangles, the area of this rectangle, and sum them together to get 6.3 inches of snow. Let's take a look at this situation in general so that we can clearly formalize why the area underneath the curve is going to give us the total distance, or in this case, the total amount of snowfall. So the question, of course, is, what if the rate of change isn't constant? So in this case, I've drawn a velocity curve which is continuous, but as you can see, is not constant by any stretch of the imagination. So go ahead and copy this down. The question is, will the area underneath this velocity curve still tell us the total distance that you've traveled between time A and time B? So here I've drawn the area underneath the curve, and what I want you to do is take a minute or two to think about, do you agree or do you disagree that the area underneath this curve is still going to tell us the total distance? Play around with it a little bit. Maybe think about how would you actually calculate this area underneath the curve? And maybe if you can't calculate it exactly, could you approximate it? And in doing so, you'll probably find that you're able to get your thoughts together and decide whether this makes sense to calculate the total distance that we've traveled. Okay, so now that you've come to a conclusion on your own, let's take a look. What could I do to calculate the area underneath this curve? It's certainly an irregular shape. So what I'm going to do is I'm going to think about splitting up this area here into small strips. Now you can clearly see that the area of each one of these strips added together will give me the area of the whole shape. So let's focus in on each of these strips. And now I want you to imagine that each of these strips are really, really small, meaning that their width is very, very small. So it takes up a very, very small chunk of time. In fact, you could almost imagine that each strip represents an instant in time. What will the area of each strip be? Well, the area of each strip will be the height times the width. And the height, because this strip is so small, will represent the velocity at that instant. So we'll multiply the velocity of that instant times the amount of time, or just an instant in time, and this small strip will then represent the distance that we've traveled in that instant in time. So each of these strips, each area will represent the distance traveled at an instant in time. And when you add those all up together, you're going to get, obviously, the total distance that you've traveled. And so, in fact, it is the case that the area underneath this velocity curve will still give us the total distance. And in thinking about how we'd actually calculate this area by cutting it up into these small strips, that will help us understand exactly why that is the case. Because what we're really doing is breaking up our trip into these miniature little instants and calculating the total amount of distance in each instant, so that we're accumulating, and the word accumulation is going to show up again and again, we're accumulating distance as we move through our trip, just as we are in real life. So now that we understand that no matter what our velocity curve or instantaneous rate of change curve looks like, we're going to be able to find the area underneath it, and that will tell us the total distance or the total amount that something has changed in that time period. We need to come up with a way to do this, and we've already begun to think about it when we cut this area up into strips. So let's go ahead and take a look at a method called the rectangular approximation method. Okay, so the area under a non-negative curve, and I say non-negative, we'll look at curves that go into negative y values soon enough, but for now, a non-negative curve will do just fine. And this is called the rectangular approximation method, also known as a Riemann sum approximation. This is named after the mathematician Georg Riemann, one of the most famous mathematicians in history. And of course, these are approximation methods, meaning that we're going to be finding an approximation, not a true value of the area underneath the curve, and these are pretty efficient methods by which to do so. So I'm going to go along, I've constructed a graphical representation of this situation, given a non-negative function, y equals f of x, on the closed interval from a to b. We can approximate the area under the curve and above the x-axis between a and b by doing the following. So I'm approximating the area underneath the curve between a and b, this area here. And what I want you to do is copy down this graphical representation. I'm going to go through and describe each step of the approximation method graphically as we go through. Alright, so before we go through the whole method, it's important to just think about, in essence, holistically, what are we doing? If you remember what we just discussed, taking that irregular area that we had underneath that velocity curve, we split it up into smaller strips. And that's what we're going to be doing here. We're going to split our area up into smaller pieces, and we'll use an area that we can easily calculate, in other words, the area of a rectangle in each strip, to find that area and then add them all together to find the total area. So the first thing we're going to do is we're going to divide the interval from a to b into n equal subintervals. And you will either be told the number of intervals that you need to split up your area from a to b into, or you'll have that option to choose on your own. In this situation here, I'm going to choose to split up my interval from a to b into 4 equal subintervals. So here you can see I've split them up. Here's one subinterval, second, third, and fourth. And you can imagine what this might be. So imagine a was 1 and b was, let's say, 3, for example. So this would be from 1 to 1.5, from 1.5 to 2, from 2 to 2.5, and from 2.5 to 3. Those would be my subintervals there. Now that I have my subintervals, I'm going to approximate the area under my curve f in each subinterval using a rectangle, because it's easy to find the area of a rectangle. So for each subinterval, let's consider the first subinterval. What I'm going to do is I'm going to construct a rectangle that will approximate the area under my curve f for only this subinterval. So the width of my rectangle is going to be the length of the subinterval. This will be the base of my rectangle. And then I'm going to choose the height. And I'm going to choose the height to be a certain value of my curve, my function f, along this subinterval, this first subinterval. Now, if you think about my curve f in this subinterval, here's where it starts, and then it goes to about here, and that's where the subinterval stops. I'm going to choose the height of my rectangle to either be the left end, the midpoint, the middle, or the right end point of my curve on that subinterval. So I can either choose to be the point on the far left, the point on the curve that's in the middle of the subinterval, or the point on the curve that's on the right end of my subinterval, and that will be the height of my rectangle. For this particular situation, let's choose the left end. So if I'm looking at my curve only on this first subinterval, the left end point will be right here. Now, I know that this is going to be the height of my rectangle, and that the base of my rectangle will be this subinterval here. So I can draw that rectangle. Alright, so that is the first rectangle that we're going to use, and that area is going to approximate the area underneath the curve on this subinterval. Now we need another rectangle to approximate the area under the curve f for this subinterval, for this subinterval, and for this subinterval. So why don't you go ahead and pause and try creating each of those rectangles according to the method we just described using the left endpoint. Alright, so for my next subinterval, I'm looking at my curve over this subinterval, and I'm choosing the left endpoint here to be the height of my rectangle. So that will be rectangle number 2. Doing the same thing and finishing out for rectangle 3 and 4. And now I have the rectangles that will approximate the area under the curve in each subinterval. Now all that's left to do, of course, is sum the area of each of these rectangles, the n rectangles, together. And before we can do that, we need to discuss briefly how will you actually compute the area of each of these rectangles. You'll need to be able to find the height and the width. Let's discuss the width first. The width of each of these rectangles is going to be the length of the subinterval. And each of these subintervals are equal length. So all that we did is we took the distance between A and B and we split it up, in this case, into 4 equal parts, or to n equal parts. So to split something up into n equal parts, you'll divide it by n. So you'll take b minus a, the distance between a and b, and you'll divide by n. And that will be the length of each subinterval. And we're going to call that delta x. This terminology, of course, should be familiar to us. Delta means change, and so you can think about delta x as sort of being the steps in the x direction that we are taking, and with each one of those steps we're calculating the area of a rectangle. So the base of each of these rectangles will be delta x. In our example that we discussed, I said, consider A being 1 and B being 3. So the distance between 1 and 3, 3 minus 1 is 2. And then when we divide it into 4 equal subintervals, we'll have 2 divided by 4, which is 1/2, meaning that each of these bases will have a length of 1/2, or 0.5. Okay, so we know the base of each of the rectangles and how to compute them, depending on the number of subintervals. And now we want to know, how do we calculate the height? Well, that's pretty easy. We're just using the value of the function, either at the left end, the midpoint, or the right end point of that particular subinterval. So in this particular situation, we use the left endpoint. So I'm actually just going to write out, and this will be the easiest way for us to clearly see, I'm going to write out the area for this first rectangle. So think about this on your own for a second first. The area of this rectangle is going to be the base, delta x, times the height. And the height of this rectangle is the value of my curve at the far left endpoint of this subinterval, which is at A. So the area of the rectangle will be f of A times delta x. Okay, so if this is the area of the first rectangle, now the area of the second rectangle. Well, the area of the second rectangle is going to be the base, which is again delta x, times the height. Now the height is the value of the curve at the left endpoint of this second subinterval. And so think about what will be the left endpoint here. Well, if A was where we started, then the left endpoint of the second interval will be 1 delta x to the right. So it'll be A plus delta x. So the height here will be the value of my function f evaluated at A plus delta x times delta x. Alright, so here is the area of rectangle 2, and I'm adding that on to the area of rectangle 1. Now I want to go ahead and add on the last 2 rectangles and the area of those 2 rectangles. So go ahead and write those out and then go ahead and press play to check that you've done it correctly. Alright, so here are the areas of the last 2 rectangles. Notice, of course, this rectangle here, the height of it is the value of my function at this point, which is a plus 2 delta x, so f of a plus 2 delta x times delta x. And the height of this rectangle here is the value of the curve f at this point, which is 3 delta x's to the right of a, or a plus 3 delta x, and then the value of the function at that point times delta x. Okay, we're going to get on to an example in just a second, but I want to make sure that we're clear on what is meant by a midpoint, or middle of the subinterval, and right endpoint of the subinterval. So what I want you to do is redraw your rectangles if you were using the midpoint of your subinterval to evaluate the height of your rectangle, and then try and write out what the area of each rectangle would be and add them together. Alright, so the left rectangular approximation, abbreviated LRAM, is here. That's one we just talked about. And midpoint rectangular approximation will be MRAM. So if you ever see these approximations, you'll know exactly what they mean. For this midpoint here, we're looking at the height of each rectangle as the value of my curve in the middle of each subinterval. So that first subinterval will be a plus a half of delta x over 2. The second rectangle will have a height determined by the midpoint of this second interval, which will be a plus 1 delta x and then plus another half to get to the midpoint. So it will be 1.5 delta x's. The third one will be a plus 1, 2, 2.5 delta x's to get to the midpoint of that third interval. So it'll be a plus 2.5 delta x, and similarly a plus 3.5 delta x for the height of that last rectangle. Notice that the base of each rectangle is still delta x. Now go ahead and work on the right rectangular approximation for this. If you are seeing that your drawing is getting a little cluttered, it's okay not to draw it. You can go ahead and just write out what that approximation will be. And so here for the right rectangular approximation method, RRAM, we're using the right endpoint in each subinterval. So for the first rectangle, that will be a plus delta x, value of the curve there, will be my height. Again, the base is length delta x, that will always be the case. Second rectangle, I have a height given by a plus 2 delta x, that's the point at which I'm evaluating my function f. And then the third rectangle, I'm going to evaluate the function at a plus 1, 2, 3 delta x. And finally, the right endpoint of the last subinterval, that last rectangle, is just f of b times delta x. So notice I have a lot of variables going on here, and this is just so that in general we know what we're doing, and you can always refer back to this. But in practice, it'll actually be a lot smoother, I think you'll find. So let's go ahead and take a look at a couple of examples. Alright, so let's check this out. A particle starts at x equals 0 and travels along the x-axis with velocity v of t equal to t squared. Use a left rectangular approximation method with 6 equal subintervals to approximate where the particle is at t equals 3. Go ahead and try this on your own first. Sketch out a graph if you'd like. Refer back to your notes if you need be, and then we'll take a look together. Okay, hopefully that went well. Remember, we need to make sure we have a plan of attack here. We want to know where the particle is at t equals 3. Let's just say after 3 seconds. And we're given the velocity function. And we also know where the particle is at the beginning. So when time is 0, it's at x equals 0. Now it'd be great if we had the position function. We can just plug in 3 into the position function, but we don't. All we know is the velocity. Luckily, we know the area under the velocity curve will tell us the total distance that it has traveled over the first 3 seconds. And so we can add on that total distance to 0, and that will tell us where the particle is after 3 seconds. And I'm going to use a left rectangular approximation method. Now, if you feel really comfortable and you don't need to visualize it with a graph, you don't have to draw out a graph. But I find it to be incredibly helpful. So I'm going to go ahead and sketch a graph of the velocity curve that I'm going to find the area underneath. Okay, so here's my curve, and I want to find the area underneath the curve over the first 3 seconds, so from 0 to 3. And when I have that area, that'll tell me the total distance that my particle has traveled in that 3-second span, and I can add that to its starting position to find where it is after 3 seconds. So following my approximation method, first thing that I need to do is split up my interval from 0 to 3 into 6 equal intervals. And this is going to determine my delta x. So delta x is going to be 3 minus 0, which is just 3, over 6. Or in other words, each of these delta x's is going to be half a unit, right? So I think about my my starting point at 0, and then delta x, or one interval to the right, will be at 0.5, the next one will be at 1, then 1.5, then 2, then 2.5, then 3, right? They're all going to be equal subintervals, each with a length of 0.5 seconds. And I can go ahead and draw this out if I want to. I can draw out the rectangles, and I'll do that here just in case you want to make sure that you can see them. Remember, I'm using the left endpoint, so on my first subinterval, let me just mark these intervals here. So for my first interval, I'll be using the left endpoint. And that left endpoint is actually at 0, right? V of 0. So when I draw this out, I'm going to have a rectangle that isn't really a rectangle. It doesn't have any area whatsoever. And then I can go through and draw the remaining rectangles. I encourage you to do that now. So there are my rectangles. I know that the base of each rectangle is the length of one subinterval, delta x, and the height is going to be the value of the curve at each left endpoint. So I can now write out what the area of each is going to be, and I'm going to write it out first representing the height of each using my function v of t, just to make sure we remember where we're getting that value from. So there you have my left endpoint approximation, and notice of course that v of 0, v of 0.5, v of 1, all of these represent the height of each rectangle, the value of my function v of t, and 0.5 is simply the base of each rectangle, or the length of each subinterval. So because my function tells me to square whatever the time is to get the velocity, I'm simply going to take the time and square it for each to find the value of each of my v of whatevers. So I'll go ahead and do that and then multiply to find the area of each and add them all together. So you can go ahead and do that now and check that your answer is correct. All right, so squaring all of these values and multiplying by 0.5 and then adding them all together gives me 6.875. And of course, I have to interpret this in terms of the problem. And this is the approximation for the area underneath the curve from 0 to 3, and the curve represents velocity. So this is the total distance that I've traveled, or the particles traveled, from 0 to 3 seconds. And of course, this is an approximation, so approximately 6.875 units to the right. Now it started to the right because it's positive. Now it started at x equals 0, and then it traveled 6.875 units, so now it's 6.875 units on the positive end of the x-axis. Last thing before we move on is I want you to think about whether or not this approximation that we made is going to be less than or greater than the true position of the particle at t equals 3. And your hint here is to look at the visual that we've drawn. To think about whether we're underestimating or overestimating the position, all we have to do is take a look at the area that we computed and see whether or not that area that we computed is going to be less than or greater than the area, the true area underneath the curve. And notice that we're under approximating because there are these little triangular, they look triangular, not quite triangular because this is curved, these little pieces of area that we are missing from the true area underneath the curve. And so the total distance that we get is going to be a little less than the true total distance that the particle has traveled. So this would be an underestimate of the true position of the particle at t equals 3. This is a question that the AP test people like to ask quite a bit, and so it's important to start thinking about whether our approximation will be an underestimate or an overestimate of the true value. All right, let's take a look at one more. All right, go ahead and try this problem out on your own. It's about water leaking out of a cup, and we'll take a look at the solution together when you're finished. Okay, a couple things that I know which are important. I'm given some specific values of the rate at which water is leaking, and I know that at the beginning there are 250 milliliters of water in the cup. I want to know how much is left after 5 seconds. So I've got to find how much water has leaked in total in those 5 seconds. And so I know that if I find the area under the curve of the function r of t from 0 to 5, that'll tell me the total amount of water that has leaked in those 5 seconds. And so I can subtract that amount away from the 250 that I started with. Now I also see that I'm not given the function, I'm just given some select values of it. But that's okay because for our approximation, we just need to know selected values of our function itself to construct our rectangles. So it can be helpful here to plot this data on a graph at least the first couple of times you're given a table of values. But if you're feeling really comfortable with this, you actually don't need to construct any graph whatsoever. I'm going to do one very quickly just so you can see what I'm talking about. There are
are my data points, and I can imagine a smooth curve connecting through these data points, if you will, but I don't need to. All I need to do is use my right-hand rectangular approximation method, and I want to split this up into 5 equal intervals, so I'm going from 0 to 5. Obviously, splitting that up into 5 equal intervals means each interval will be of length 1. So my first interval will be from 0 to 1, and I'm going to use the right-hand approximation method, so I'm going to use the value of my function r on the right endpoint of my subinterval, which in this case will be at 1. So there are my rectangles. Notice each one has a height that is determined by the value of the function r of t on the right end of each interval. Alright, so now I can use the values of my function r and the fact that each interval is length 1 to compute the area of each rectangle and add them together.
All right, going ahead and computing the area of each of these rectangles is fairly straightforward. Make sure that you're using the right endpoint. And since your intervals are of length 1, that's very easy as well. You're just multiplying the value of your function r at each right endpoint by 1, and then adding together. And you'll end up with 25 milliliters. It's important to understand what this means. This is the total number of milliliters that you approximate have leaked from the cup in the first 5 seconds. So your answer is going to be the value of water that you had in the cup at the start minus the approximation you have for how much has leaked. So my conclusion is that there's approximately 225 milliliters remaining after 5 seconds. We can now move on to the homework, 7.01. But if you'd like to see another great example where this is actually applied in real life, check out page 275 and 276. The example deals with the medical field and measuring how your heart is working.